This is the actual process of moving.
Okay.
But what does that mean in this situation?
Okay, good afternoon, everybody. Usually left a note somewhere. I guess we're about ready to get started. So just before we get started, I know your test is coming up this week. Does anybody have any questions? No? Okay, so things seem nice and clear there with the test. So last day we talked more about Gaussian surfaces. We defined electric flux, and that was a quantity that tells us how many electric field lines cut through an area. We said that there is a general way to calculate flux, which is the integral of E dot dA. You use this in cases of a non-uniform electric field or an odd-shaped area. And if we have constant fields in areas that are symmetric, we can skip the integral and just do the scalar product E dot A. So that's how far we got last time. Today we're going to take Gauss's law, apply it to spherical symmetry, and use that to show how we can use Gauss's law to find electric fields, as long as we know about the shape of the electric field lines. So that's what we're going to get going with today. So let's start. We'll think about a positive point charge Q. So we have a small positive charge. We'd like to calculate the electric flux through a spherical Gaussian surface of radius r centered on the charge. So this is going to be a flux calculation. So how we're going to get started, so I drew my point charge, I drew my electric field lines. So these lines coming out of the charge are the electric field lines. This part tells me my Gaussian surface. It's a spherical Gaussian surface of radius r. When we have a point charge, we assume that's spherical, so we use a sphere for a Gaussian surface. So the next thing we'll do is draw our Gaussian surface. That's my version of a perfect sphere. It's a little bit squishy, but hopefully you get the idea. So I'll label that r for radius. And then we'll write in that this is our Gaussian surface. Which is a sphere with radius r. And whenever we do Gauss's law problems and flux problems, you'll always have to draw your Gaussian surface. That's a really important part. So now what we're going to do, we know we want to calculate flux. We know we have two ways to do it. We can do the integral or E dot A. If we take our radius to be one specific radius, one constant value, then our electric field is going to be a constant value. That's going to let us do E dot A for our flux. Okay, so let's limit ourselves to that. So we're going to say that R is constant. And if R is constant, then our electric field, which we know is KQ over R squared, is also constant. So now we're in a situation of calculating flux where we have a constant electric field and we know what our Gaussian surface is, the area. All right, so let's get started on the flux. So our net electric flux is E dot A. All right, this is a scalar product, so it's a scalar product between two vectors. If we want to do the scalar product, we have to identify that we know that they're vectors and which way do they point. So our electric field is radially outwards. So our electric field vector is radially out. So this vector is radially outwards. What about our area vector? Well, we know area points straight out from the surface. So our normal unit vector will point straight out, which means our area vector is also radially outwards. So both E and A point radially outwards from our surface.
I have a silly question. does radially outward just mean along the radius, or
Yeah.
what does that mean?
Radial means along the radius.
Okay,
Yeah.
makes sense.
Yeah, just like left means to the left, kind of same deal. Okay, so since they're both radially outwards, both of those vectors are parallel. So when we write down our scalar product, which is E times A times cosine theta, two vectors that are parallel, the angle between them equals 0. Okay, so this gives us our electric flux then is equal to E times A. Let's put in what we know for E. Let's put in what we know for A. E stands for the magnitude of our electric field, K times Q over R squared. A stands for the surface area of our Gaussian surface. Here's where you have to remember some of your basic geometry. The area of a sphere is 4 pi R squared. Okay. I'm going to take this one step further with my K. And I'm going to remember that when we wrote down K the first time, we said K was 1 over 4 pi epsilon naught. So I'm going to put that in for my K value. 1 over 4 pi epsilon naught times Q over R squared times 4 pi R squared. So there's my expression for my electric flux. So 4 cancels, pi cancels. This is interesting. R squared cancels. So that's kind of an interesting result. We started off by saying that our R was constant, but it looks like it cancels, so it's kind of okay that we did that. Okay, so let's finish and write down our answer. Our net electric flux through a sphere with radius R around a point charge Q is equal to that charge Q divided by the permittivity of free space epsilon naught. Okay, any questions? We can and will do this sort of calculation for other geometries of charge as well. We'll start with the point charge, the first one. Any questions? If you look at the printed slides, the next one is a homework problem that just has you filling in Q and epsilon naught to do a calculation. So we'll skip ahead and do a couple of conceptual questions. But I will post the answer to that homework question. So let's ask some questions about that result that we just got. If you printed off the slides, you wouldn't have boxes around yours. When I was looking at the slide, I didn't like it, so I just drew in the boxes myself. You can draw them or not as you see fit. So the result we just got, why don't we just summarize that? Our electric flux was E dot A, which was Q over epsilon naught, where Q is our point charge, which is inside the surface. And we remember that flux is a quantity that represents the number of electric field lines going through a surface. So let's ask if the net electric flux doesn't depend on how big the Gaussian surface is. Okay. So what do you think? If I picked a small r instead of a big R, would I get the same flux or a different flux?
Same flux as long as it's not changing.
Okay, so I got an answer for same. Who agrees? Who doesn't agree? Okay, so let's look at that answer and let's put it in terms of this definition of the electric flux. So what I'm going to do is I'm going to take this picture and I'm going to draw two Gaussian surfaces. So there's my first surface. It's got a radius of R1. If my Gaussian surface represents the number of lines through the surface, let's count the number of lines through the surface. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 lines through this surface. Okay, let's draw a different Gaussian surface with a bigger radius. So here's a second radius, R2. How many lines cut through this surface? 8 lines through this one, right? So the answer to this question, does the flux depend on the size of the Gaussian surface? The answer to that question is no. Okay, so it is kind of built into this equation right here, but hopefully this explains physically why that's a true answer. For what it's worth, I've put this question on at least 2 tests or finals in the past. I think this is a good question to check, do you understand flux? Okay, next question. I drew a spherical Gaussian surface. Does the flux depend on the shape? What if I didn't draw a sphere? What do you think?
No.
Okay, so one answer for no. Who agrees with no, it doesn't depend on the shape? Anybody disagree? Okay, so we got some answers there. So let's have a look here. I'm going to draw my first one, R1. If I count the number of lines, I get 8 lines. I'm going to draw my second surface. I'm going to make this one a cube or a box. I still have 8 lines going through the box. Okay, so no matter which shape I pick, I still get my 8 lines. So my answer to this question is no. Okay, that's also hidden in the equation. Q over epsilon naught doesn't have a variable for what's the shape of my box. And some people like math explanations, some people like picture explanations, kind of all good. Okay, does the flux depend on the location of the charge? So my charge has been at the center every time. Did it have to be at the center? What do you think? Does it depend on where? Okay, I got some no's, some yeses, and some kind of not so sure
I don't
looks.
think so.
Okay, so another no for sure. So I'm going to draw my 2 surfaces. I'm going to draw R1. I'm going to make this one just a little bit smaller for convenience this time. R1, I've got 8 lines. Now I'm going to draw another sort of sphere, more of an egg, but I'm going to have it close to the charge on one side and far away from the charge on the other side. So this time it is not centralized. I still got 8 lines. So the answer to this question is no again. So our flux, and this is going to be the next part we're going to look at. Right here I said, does the flux depend on the location of the charge within? That word within is actually very important.
Because if it's outside the flux, then you don't have all 8 lines.
There we go, and that's what we're going to get at. All right, so it doesn't matter the size, shape, or position within, but it does have to be within. Okay, so that part's really important, and we're going to go through that part next. So if we're saying the flux, or if the charge has to be inside, then the kind of natural question is, well, what happens if it's outside? So let's put a charge outside, and let's ask about the flux when we do that. So what if we take our point charge and we put it outside a Gaussian surface? So underline the word outside. So we remember the definition of electric flux, the number of electric field lines cutting through a surface or penetrating a surface. It's important to recognize that the total number of flux is a total number. So you have to take the number of lines that go out and subtract the number of lines that go in. So it's a net number of lines. If one goes in and it goes back out, then the total flux would be 0. If more go in versus more go out, it wouldn't be 0. So let's draw our surface. I picked a cloud shape because that was easy to do in PowerPoint. And we said that it didn't matter what the size or shape was anyway. So there's my Gaussian surface. Next, I'm going to draw my electric field lines from that charge. So my electric field lines go radially outwards. where are my electric field lines? So if we look at this picture, so this line goes in and comes out, this one goes in and comes out, this one goes in and comes out. So every line that goes into that surface cuts back out through it. And no matter how many lines you drew, you would see that every one that goes in also goes back out. And that makes sense when we think about what we drew for electric field lines when we put up those positive charges and negative charges. Lines can only start on a positive and they can only stop on a negative. The only way they'd be allowed to stop inside is if there was a negative charge inside, but there's nothing inside, so they're not allowed to stop inside. So anything that goes in has to go back out because there's nowhere for it to stop. So they start on a positive, start on a negative. That means nothing starts or stops inside. So let's get some notes now. So for any closed surface, if there is no charge inside, so we'll say if Q enclosed, so Q enclosed means the total amount of charge inside the Gaussian surface. If that's equal to 0, then that tells us that no electric field lines start or stop inside. And if that's true, then every line that goes in also comes back out. So the conclusion is that the net electric flux, if the charge is outside, must be 0. And I think this goes with a question on the assignment about this chapter. Okay, so you've got some charges and some spaces and you've got to figure out the net flux. Some of them are going to be 0 because some of those surfaces don't have any charge inside, so that will help with that assignment. So our conclusion then is that total electric flux is only ever a result of the charges inside. Yeah?
Okay, well, that kind of just answers my question.
Was that it?
Say, like, lines cutting through would make me think that, like, you got some positive going on, but nothing's stopping it, which would make me think a net positive, right? So, like,
It's almost like if I give you $10 and you give it to your friend, your net money is 0. So you had 10 in, you got 10 out, now you got nothing.
right.
Yeah.
Okay. It's only if they stop, or like something changes with the path inside.
Yeah.
That's when there's a flux.
Exactly.
Okay.
Yeah, okay, great. Yep,
What would be an example of it stopping inside?
if I had a negative charge in here, so it would go from that positive to the negative.
So there will have to be a charge in there regardless to make it non-zero.
Yeah, the only way to get a flux that's not 0 is to have a charge inside, like when we answered all those what's in the box questions.
And in that case, it would just be 3 minus 1.
Yeah, and
So
we'll
net would be 2.
we'll kind of do that on our next page now, how we calculate the flux when we have assorted charges inside. Okay, we're good to move on from here? Yes. So now we'll say, what if we have multiple charges, both inside and outside of, and I put arbitrary here, so inside of our Gaussian surface, remembering that we can draw whatever we wish for our Gaussian surface, any size, any shape, kind of wherever the charges are in the middle. So the first thing I'm going to do is draw my Gaussian surface. I'm going to leave some charges inside and some charges outside. So here's a picture of my Gaussian surface. Our goal is to find the net electric flux through that surface. So the first thing we'll say is that the charges outside have no impact. Okay, so for the charge outside, every line it makes going through that surface also leaves. So there's no contribution due to the outside charges. That means we have to deal with the inside charges to get the total electric flux from the inside charges. This one will make a flux, that one will, so will that one, and that one. If we find each one of those fluxes and add them up, then we get the total flux. So we find the flux due to each charge, add them all up, then we've got the total. recognizing that some of them are gonna have negative and some of them are gonna have positive, so we get a net flux there. Okay, so every charge inside makes a little bit of flux. That little bit of flux is the integral of E dot dA. I wrote down the integral form here because we have this weird shape and the charge is at all these weird positions. And that flux overall is the charge divided by epsilon naught. So every single charge makes a flux that's equal to Q over epsilon naught. Then our total electric flux is the flux due to the first one, flux 1. So if this is my charge 1, then flux 1 is Q1 over epsilon naught. Then I add on the flux due to the second one, let's say that's this one, which is going to be Q2 over epsilon naught. I'll add on the flux due to the third one, flux 3 equals Q3 over epsilon naught, plus blah, 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 until we add them all up. Okay, so we add up all the fluxes to get the total. Let's fill in that the flux is charge over epsilon naught. So here we'll put down our proper definition of Q enclosed. So we've got 1 over epsilon naught times Q1 plus Q2 plus Q3 until we add up all the charges. When we add up all the charges, we get the total charge inside. That's what we call Q enclosed. So define. Q enclosed equals Q1 plus Q2 plus Q3 plus all of them until we get the total. And that's equal to the net charge enclosed by the Gaussian surface. So when we're working on this Gauss's law section, sometimes students have trouble choosing the Gaussian surfaces, and typically you're going to make it match the symmetry of the charge. Sometimes people also have trouble identifying how much charge is inside the surface, or remembering that it's only the charge inside that matters. So those are kind of two key things to make sure you keep straight. Your Gaussian surface has to match the shape of your charge, and we only care about the charge inside. The outside stuff has no contribution at all. So we'll put this together and write down Gauss's law, which says that the net electric flux, you can find it as the integral of E dot dA equals Q enclosed over epsilon naught. Here's our general form. And then we also have our specialized cases of net electric flux is E dot A equals Q enclosed over epsilon naught. So those are our specialized cases of constant electric field with areas that are symmetric. So I think I'll just call these simple cases. Okay, questions to here?
What would be an example of a complex case for this where we have to find the integral?
Around lines of charge, we'll do that one. Yeah, the electric field won't be constant there. You could also get an electric field that depends on position, right? So it could depend on X or Y or Z. Yeah, for sure. Okay, so now that I've got plus and minus charges in here, I'm going to stress again that your net electric flux can be positive or negative. Your book says the flux into a surface and the flux out of a surface. I think your book shouldn't say that because that gives a direction to flux. Flux does not have a direction, it's a scalar. If it's negative, it means more lines come in. If it's positive, it means more lines go out. So the sign of the flux does give you an idea of the direction of the electric field lines, but the flux does not have a direction. The last thing that I think is kind of interesting, our expression for flux here, it's a half of one of Maxwell's 4 equations. So we're going to spend a whole bunch of lectures just talking about a half of one equation. I think that's kind of neat. And that sort of happens in physics more often than you care for. Okay, questions? All right, so let's do some examples. I nabbed this picture out of your textbook because I think it's kind of a really good example. So the figure shows the electric field around a dipole. Remember, that's two small charges, equal and opposite signs, separated by a small distance. These red lines here show the electric field lines. I mean, those previously. Find the net electric flux through each of the four surfaces in the picture. Okay, so we'll start by thinking about the flux through surface A. So I'll trace surface A. And we'll write down what we just got for Gauss's law. Net electric flux equals the integral of E dot dA equals Q enclosed over epsilon naught. So maybe take a moment before we say the answer out loud to write down on your paper what you think the answer is. The writing it down step is important because then you actually have to commit to an answer. You can't kind of go between a couple of answers. You can always erase it if you're not right. Okay, anybody want to share what they got for their answer?
So we know that Q enclosed should be all the lines that are leaving subtracted by the lines that are entering, and I
Yeah.
don't see any lines entering. So it's just the addition of all the lines.
Okay, so what are we going to write down for our answer? Flux equals. Does anybody else have an answer they want to share? Yeah?
0.
Okay, I got an answer of 0. Anybody else write down 0 and wish to share? Okay, anybody write down something different? Yeah?
I wrote a positive.
Okay, a positive what? Just positive.
Just positive.
Yeah, okay, so we got positive.
No numbers, so.
Yeah, with no numbers. Well, you can still write it down in symbols. We're going to do lots of problems that are just symbols.
Okay.
Yeah, even though I know people don't like them, we're still going to do it.
Q by epsilon naught.
Okay, I got an answer of Q over epsilon naught. Anybody write that down? Okay, so these problems are kind of complicated, right? You know, we don't have a clear consensus. So what we have to do, and this goes back to where I said people have trouble identifying what's the charge inside, and that seems to be happening here. So we know we're talking about surface A, so something we can do is get rid of everything else. Let's simplify. So let's stop looking at anything except surface A. Now we look inside surface A, and we ask, how much charge is inside surface A? Okay, maybe it's a little bit clearer once we cover up the rest of the visually distracting stuff. There's one charge inside there, right? Plus Q is the only thing inside there. So Q enclosed is equal to plus Q, and then we have to include our constant. Okay, makes sense? Okay, so that's one of 4. We'll do B next. So if we're going to do B next, first thing I'm going to do is trace out surface B. I'd like to find the electric flux. We know that that's Q enclosed over epsilon naught. Okay, so take a moment to write down in your notes what you think the answer is. I think we might get a little more uptake on this one. Okay, anybody ready to share what they think the answer for this one is?
Negative Q over epsilon naught.
Okay, so the first answer is minus Q over epsilon naught. Any agreement?
I do.
Lots of agreement here with this one. Okay, so I think hopefully that time everybody kind of put into practice. Let's isolate B. Let's look at it all by itself. What's inside? Negative Q, and that is indeed the correct answer. Oh, somebody likes a little bit of T-sizzle. All right, let's move on to part C next. Okay, any questions about this one before we move on? Good? All right. Find the net electric flux through surface C next. So let's trace surface C, that's the whole kidney bean. Net electric flux equals. Okay, so jot down your answers for this one.
I think it's 0.
Okay, so the first answer is 0. Do we have agreement with 0? Okay, lots of nods for 0. Disagreement? Okay, so it's Q enclosed. That means the total amount of charge, or total amount of charge inside this surface is, we have a negative 1 right here, and we have a positive 1 right here, divided by epsilon naught, and you get 0. Okay, so whatever your charges inside are, you have to add them all up. And then we've got one more to do. Okay, surface D is going to be our last one. Let's trace out surface D. We have the net electric flux through this one. Jot this one down in your notes.
It's 0 as well, because leaving minus entering is 3 minus 3, so 0.
Okay, so suggested answer of 0. Does anybody agree? Lots of agreement here. Okay, so you can think about it from the number of lines. It's absolutely correct. 3 go in and 3 go out. We can also go with our definition from Gauss's law, the amount of charge enclosed. And you'd be shocked how many times this throws people. This totally stumps people. You look at this Gaussian surface and there's nothing inside, and I say, what's the charge inside? And people like, don't know what to tell you, right? They're just completely lost. So you look inside your box. If there's nothing inside the box, then there's nothing inside the box. That means charge is 0. Equals 0. Full epsilon naught equals 0. Okay, so empty boxes can be a stumper, but empty is empty. It doesn't have any charge at all. Okay, still good? Okay, let's move on to another example. So we have a charge of 170 microcoulombs. So this is going to be our charge Q. And it's at the center of a cube with edge length 80 centimeters or 0.8 meters. So my charge is in the center. Center is about here, like in a 3D picture. So there's my charge Q. No other charges are nearby. So this is the only charge that matters in this problem. First thing we're asked to do is draw the electric field of the point charge. It's a point charge. The electric field lines are radially outwards. So that one's not too tough. The box doesn't impact this at all. We happen to be drawn through a box, however. The lines are still radially outwards no matter what surface we drew. Okay. There's part A done. Part B, find the total electric flux through each face of the cube. So let's think about our Gauss's law. Net electric flux through one face is equal to the integral of E dot dA. So that's the flux through one face. We did examples like that last class. You know, we had a square, we knew what the electric field was, find the flux through that surface, we did E dot A. This one's weird though, right? We've got a radial electric field and a flat surface. This one's hard. Not impossible, but this is hard, right? So if you've been doing math for a few years, you love to integrate, you're probably going to do this as a fun challenge. I'm going to think ahead, and I'm going to ask, if I did part C first, would it make part B easier? Okay, so I'm going to try that. So I'm going to try part C first. And in part C, I know that my total electric flux through the entire cube is equal to the charge enclosed by the cube divided by epsilon naught. So I've got a big closed surface, I have a charge inside, the flux is just Q over epsilon naught. We already established it didn't matter the shape of the surface, where the charge was, or the size of the surface, it's just Q over epsilon naught. So my net flux through the entire thing is my charge, 170 times 10 to the minus 6 coulombs, divided by epsilon naught, 8.85 times 10 to the minus 12 coulombs squared over newtons meters squared, to get a total electric flux of 1.97 times 10 to the 7 newtons meters squared per coulomb. Okay, so there's a scalar answer, no direction. Positive because we have a positive charge inside and the lines are coming out. So there's the total flux through the entire surface. Now let's back up to part B. Find the flux through each face. So our charge is dead smack in the middle. So everything here is symmetric and a cube is symmetric. If a cube has 6 faces and everything is symmetric, then the flux through one face is 1/6 of the total flux, just because everything is symmetric. So we'll come back to B. Cube, 6 faces. Everything is symmetric. So the flux through one face equals 1/6 times our flux total. Okay, I put in some awkward looking subscripts there, but hopefully it's going to help keep it clear. So 1.97 times 10 to the 7 divided by 6, and we get 0.320 times 10 to the 7 newtons meters squared over coulombs. So this is hopefully going to get used to thinking about symmetry and how you can use symmetry to solve problems. And then part D is interesting. Would our answers to A, B, or C change if we made the charge off center? So that's kind of interesting. Before we answer D, I'm going to redraw my charge and my box. I'm going to do a 2D projection because 3D is hard. So if the charge is centered, then my charge is right here. It's at the center of my box. And my electric field lines point radially outwards. And so that's if it's centered. If it's off center, then I've got my charge here, but now my box is more like this. I'll redraw my electric field lines. Everybody okay with the picture? Okay, and I'm going to use this picture to help me answer the questions. So, part A, did the electric field lines change? I gotta say no, the electric field lines didn't change at all because of where I chose to draw this box. So A, no change. The electric field lines are radially outwards no matter what your Gaussian surface looks like or where that charge is. That doesn't affect the electric field. Okay, part B, the flux through each face. If we look at the two pictures, if we remember flux represents the total number of lines, are these two different if we think about the flux through one face?
They look different.
I think they're different. So if we look at this picture, we've got one going through the center and one going through each corner. If we look at this picture, we have one through the center only. If we look at this side, we've got one through the center, one through each corner. If we look at this one, we have 3 going through the side. So I think the flux through each face is different here. So I think it's different. So B is different. And then C is the flux through the entire cube. Is that the same or different? That one's the same, and this is one of the ones we went through. Did it matter where the charge was? 8 lines, 8 lines, so the total electric flux is the same. Okay, so that takes us through things conceptually. Any questions? Okay, So, next, we're going to apply Gauss's law to conductors. So before we're able to do that, let's summarize some of the properties of conductors, because that's going to help us apply Gauss's law and understand what's happening. But first we have to establish that we're going to talk about conductors in electrostatic equilibrium. So that's where we're going to focus in for a little while. When we get into our chapter, when we talk about capacitors and resistors and circuits, we're not going to be in equilibrium anymore, but for this part, it's all electrostatic equilibrium. So here, the part of the word electro, that means charge. Equilibrium means not moving, or sorry, acceleration is 0, constant velocity, and static means still. Velocity equals 0. Okay, so there's a lot of physics in that phrase, electrostatic equilibrium. What it means is that every charge in our conductor is staying still. It's not moving. So wherever those charges are, they don't go anywhere. They stay perfectly still. So if our acceleration is 0, we're going to think about this on the next slide. You might start to think ahead, what does that mean about the force and what does that mean about the electric field? And the properties we have of a conductor is that your electric field is 0 inside a conductor. If we have any extra charge, it's going to be all on the surface or surfaces. The electric field just outside is perpendicular, and we know the magnitude. We're going to show these first three. And for our last one, it talks about charge density. We're going to hold off till we get to our chapter on potential before we prove this one is true. But it is one of the properties, so it belongs in this list. Okay, let's deal with property 1 first. This one is pretty easy to go through. So property 1, electric field equals 0 inside a conductor, and this is in static equilibrium. So let's think about every single charge in the conductor. The acceleration is 0 because it's in static equilibrium. Then the force from Newton's second law, which is mass times acceleration, that also has to equal 0. And we remember that electric field is the force divided by the charge. If the force is 0, then the field is 0. You can also sort of think about it in reverse. If the electric field wasn't 0, then the electric force would not be 0. If the electric force is not 0, it's going to be moving around. It's going to have an acceleration. If it has an acceleration, it violates static equilibrium, and that's not what we're talking about. Okay, so if you want to think about it forwards or backwards, you still get the same answer. This kind of makes sense. This is probably fairly intuitive for an isolated system if it's away from any electric fields. But typically, we're all in electric fields all the time. So what if you have a conductor in electrostatic equilibrium inside an electric field? Totally happens, right? So if we just have a conductor by itself with no field nearby, then this conductor does have lots of charges in it. You might have a plus here, a minus here, probably a plus here and a minus here, and then you get a plus and a minus. The charges are all sort of randomized, right? Randomly distributed, and things aren't moving. That's kind of okay. But what if we add an external field? So in an external field that we might call E external. And then I'll draw that field. Let's think about what happens to those charges then. So we have these charges, they're in an electric field, so they feel an electric force. Our positive charges will be pulled along with the field, so they're going to get pulled over to this side. That's where our positives are going to end up. Oh, that's not very bright at all, I'm sorry. I drew plus signs on this side of the diagram. I didn't realize it wouldn't come out up here. Our negative signs will feel a force opposite the electric field, so our negative charges are going to end up over here. So this side ends up negative, and this side ends up positive. Because those charges have been pulled along by the electric force, which is created by that external electric field. Okay, so let's write a little bit of that down. So, charges feel electric force. So they move to one side of the conductor or the other. So charges move. Because the positive goes to one side and the negatives go to the other, it means the charges separate. Okay, well what happens if we have one side negative and one side positive? That establishes a new electric field, because electric field goes from positive to negative. So we get a new electric field that we might call E internal. So that electric field is created by the separation of those charges. So that separation creates E internal. And that opposes the E external and creates a new net electric field of 0. So E external plus E internal equals 0. Once those are perfectly balanced, the charges stop moving and the total electric field is 0 again. And then I think I'll add the note that this result, E equals 0, in a conductor, in electrostatic equilibrium, is always true. That's a result you should know off the top of your head. So you've got a test question, and the question is A, B, C, and D. Find the electric field here, 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 and here. If any of those spots are in a conductor, your answer is E equals 0 because it's inside a conductor. Okay? The only exception might be I could ask you, prove that the electric field in a conductor is 0. Then you'd have to go through the process and show it. But otherwise, you can just say E is equal to 0 in a conductor. Okay, property 2 says that the total charge is on the surface. That's pretty quick, so let's see if we can get through that before we have to quit. So I've got a conductor. I'll trace my conductor. It's this weird shape. And it has some net charge Q. If I want to figure out where the charges are, I'm going to draw a Gaussian surface just inside the surface of the conductor. Okay, so the purple line is my conductor. I'm trying to figure out something about the charge, so I'm going to draw a Gaussian surface, and I'm going to put that Gaussian surface inside my conductor, and I'm putting it really close to the surface. So inside, and by just inside, I mean really close. Almost touching the outer surface, right? So it's so close, it's right up against it. So let's ask, what's the electric field inside the conductor? We know the answer to that one, E equals 0. That's our property 1. Next, if we think about Gauss's law, net electric flux equals the integral of E dot dA equals Q enclosed over epsilon naught. If my electric field is 0, then E dot dA is 0. So the integral of 0 is just 0. That gives me that my Q enclosed equals 0. So Q enclosed, all the charge inside here equals 0. But the conductor is charged, so if it's not inside the conductor, where is it? It's got to be on the surface. So nothing can be inside because the electric field has to be 0. Therefore, it all has to be on the surface. So all charge must be outside Gaussian surface. On the surface of the conductor. And if you were thinking physically about why this is true, this also makes sense. If you have a bunch of charges, like charges, say you have a bunch of negatives, they feel an electric force which repels them. They're going to spread apart until they're as far apart as possible. The way to get as far apart as possible is to go to the surface. So it makes sense with what we know about charges. Okay, that takes us up to almost 12:50, so we'll quit there, and we're back again on Wednesday.